All right, so today we're going to talk about the alternating series test. And so the general formula for the alternating series test is the series -1 to the power of n multiplied by a b sub n. This -1 can be to the nth power, the n plus 1 power, the n minus 1 power. It doesn't really matter as long as it's n plus a constant, it fits the formula. So in our example problem, you can see that it's -1 to the nth power multiplied by 1 over n squared plus 1, thus showing that b sub n is going to be equal to 1 over n squared plus 1. So the test requirements for the alternating series are that the limit of b sub n is equal to 0 as n approaches infinity, and that the value of b sub n, the function, is decreasing. And so to test the limit, we're just going to take the limit of b sub n as n approaches infinity. You can see that it'd be the limit of 1 over n squared plus 1. When you plug in infinity, you get 1 over infinity, which we all know is equal to 0, so it passes that test. Step 2, b sub n is decreasing. You can see in a theoretical function n squared plus 1, if you were to add 1 to n, you can see that the second term is n plus 1 squared plus 1, which is inherently going to be greater than the first term because we added 1 to it. So if we transform this to fit our equation, we have 1 over n plus 1 squared plus 1 is less than 1 over n squared plus 1, which shows us that the second term is less than the first term, which means that b sub n is decreasing. So therefore, it passes both test requirements, and by the alternating series test, that example problem decreases, or that example problem converges. So the next thing we need to figure out is this conditional or is this absolute? What this means is if we were to remove that -1 to the nth power part of the equation, would it still converge? And so essentially all we need to do for that is to test, say we get rid of that -1 part, does it converge? And so what we've used here is the limit comparison test. And so we compare it to the series 1 over n squared, which we all know converges. And so by having that series above our other series, you can reverse and multiply to get n squared plus 1 over n squared as the limit approaches infinity. Now, if we multiply every single term by 1 over n squared, you end up getting 1 plus 1 over n squared, everything over 1. If you input infinity for n, you end up getting 1, since the limit comparison test states that if it's equal to 1, then it behaves the same as our comparison series. Then we know for a fact that 1 over n squared plus 1 does in fact converge, meaning that the original equation, the -1 to the n over n squared plus 1, converges absolutely.